Okay, we're talking about indeterminate expressions and variety of those indeterminate expressions, and they come from quotient rule is the main troublemaker, and just as long as you stick with the actual statement of the quotient rule, so the limit of the denominator cannot be equal to 0 in order for the quotient rule to be applicable, then you're fine. That's what we discussed yesterday, but we also discovered at the end that even when you are trying to get out of trouble and you do not apply the quotient rule as we did in here, and we do some algebra, you might end up in a different place, which is just as bad and just as good, and that is when you deal with, rather than division by 0, you end up with infinities. And they create just as much trouble or more, and the rule still applies the same way. Do not try to apply the quotient rule if the limit of the denominator or numerator is infinity, because that means that the sequence is divergent, and there is no quotient rule for divergent sequences. So, at least so far, that is why we had to do some extra algebra for the second time in order to find the answer. Okay, so that requires then a little bit more care for infinite limits. So even though it is clear what we mean by an infinite sequence with an infinite limit, we still have to be careful here. And so I just want to write up the definition of a sequence that diverges to infinity. So a sequence diverges to an diverges to infinity plus infinity. There are two, and they are certainly very distinct. F. So for any m, there is an n such that an larger than m when n larger than n capital. Okay, so in other words, it's at some point the sequence can be made as large as you like. Whatever standard of largeness you pick, that's m, will pass it. So suppose this is what we have. We pick m here. There is a sequence. No matter how it behaves initially, at some point it will pass that threshold. So there is no ceiling. So we try to, that's what we're saying here, is that no matter what ceiling we pick, m, at some point the whole tail of the sequence, this one is the tail, will be above that ceiling. Okay, so we'll go through every ceiling imaginable, and the notation is for this statement, an arrow infinity as n goes to infinity, or once again with the limit as we have lim notation that we have used before. Okay, so that is a very specific definition. It is, in a way, resembles the definition of the limit of which as a number, but except epsilon, and we are trying to get as close as possible to the limit. We are trying to get as close as possible to the limit, which happens to be infinity, and that's why we have to push ourselves not towards some kind of a convergence or an accumulation of values, but rather we are pushing towards infinity that we do not see. So in other words, we are trying to getting closer and closer to infinity is what this definition is saying. So accumulation towards a number gives you some oscillations that disappear, roughly speaking. So it fits into a band around number L. So if you remember those discussions. So and here we're talking about a band next to a band around infinity. Okay, so if it was actually the case, which it's not, but imagine for a moment that infinity is a number, so then, well, if this is infinity, okay, so then what does it mean for us to approach infinity? It means that this is how we're going, like this. we can never reach infinity equal to infinity because the sequence itself is made of numbers, so it will never actually take the infinite value, but that's how it is getting closer and closer to it. And then once again, that understanding that we have to, no matter how narrow a band we put around that location, we finally will get into it, and the whole tail of the sequence will stay within that band. That's what this picture indicates. Except, well, think about it. If we're talking about infinity, which is not something that we can even put on the xy plane, because it's not there. It is infinite. XY plane only is entirely about numbers. So then, what is that band we're talking about? That's what the band is. This is the band. Okay, so trying to get closer to infinity means that we're getting away from zero. Okay, so then this line y equal m slides in the vertical direction on, and no matter how far we slide it, the sequence eventually will pass it and stay above it. Okay, so then naturally we have the other one going in the opposite direction. So once again we have a sequence an, and this one diverges to negative infinity. And it's almost identical, except we are pushing ourselves down rather than up. And so that's the only sign. The only change is the symbol of inequality. Larger is replaced with less. Okay, so the definition matches your definition of what? In Calculus 1, in Calculus 1, remember what this is related to in Calculus 1? When does a function, so we're talking about sequences, but if in Calculus 1, if you talk about functions in a similar manner, and you say function goes to infinity, what is that we're talking about? It could go to infinity, so that is certainly a possibility. A function like that, y equal x squared, and its limit at infinity is infinite. Okay, but there was another one. Remember vertical asymptotes? So it's the same story. So here x is approaching a. This is a. Then how do you describe that limit? How to describe this behavior? Or you verbally describe it as a vertical asymptote. Graphically, this is how you illustrate it. But if you want to actually do algebra, this is how you write it up with either one or the other statement. Well, the picture that I have actually refers to the first one, because this one goes to positive infinity. But the examples such as well, how about tangent? That's not a tangent. This is tangent. So this is tangent, and tangent. Each branch of tangent has this two asymptotes on two ends. Okay, so this is negative pi over 2, and this is pi over 2. So if this is tangent, then I describe this behavior in the manner exactly similar to what we're just talking about, except well, it's about functions. But let me write it out anyway. So limit tangent x goes to say negative pi over 2 plus is equal to negative infinity, and limit of tangent x goes to pi over 2 minus, from the left or from the right. As you can see, the behavior has to be specific here, goes to positive infinity. Okay, so then I'm talking about this is visible here, and that one is visible there. Okay, so once again, if I had all the rest of the branches of tangent, you would see that it doesn't matter from which direction we approach the asymptote. But what actually is how do we connect it to sequences? And this is how I could just take and put a bunch of points, sequences, on the graph like this. And it keeps on with the graph of tangent. Okay, so then how do I describe the behavior of the sequence? I describe it in the same manner. I say that the sequence goes to infinity. So, well, that is the connection to calculus 1. Okay, so one problem, another connection to calculus 1 is what to do about those fractions when the fractions, rational functions, when the denominator and the numerator both go to infinity. So I wonder if you remember this one. Say x cubed plus 3x minus 1 over 2x cubed plus 3n squared plus 2. What is the limit of this as x goes to infinity? That's right. How do you know? That's right. So the degrees coincide, right? The degree of the numerator is 3, denominator is also 3, which means that what you pay attention to is the leading terms. So these are the leading terms, and they determine the long-term behavior of both of the polynomial and the numerator and denominator. So and then altogether, what you do, you actually throw out the rest of the terms, non-leading terms, and then you end up with x cubed divided by 2x cubed, which gives you 1/2. Okay, so that's roughly how it works out. But you do notice that the limit of the numerator and the denominator is infinite. So if you try to proceed on from this, following the quotient rule, you will end up infinity over infinity, which is an indeterminate expression, in which we do not accept as the answer. So then, once you see that, you walk all the way back and start over in this doing this algebraic stuff. Okay, but it's also possible that you if you change the degree, say like this, I only change the degree of the denominator, like this. Okay, so then the degree of the numerator is 3, which is higher than the one of the numerator, and the answer is then infinity, right? In fact, positive infinity. So what is this? So that comes from calculus 1 for the most part, and the only thing that we want to add to this is that we just replace each x with n, and we can speak of sequences. So this will be exactly the same thing if I'm talking about sequences. N cubed plus 3n minus 1, 2n squared, 2n cubed plus, I keep changing here, sorry about that. So this is all about x. And now I'm switching to n. 3n squared, 3n squared plus 2. This one goes to 1/2. But the other one is n cubed plus 3n minus 1, 2n squared plus 3n plus 2. This one goes to infinity. So that the last one requires this new definition that we have discussed. So in other words, infinity over infinity, indeterminate. Bad news. But there are others, 1 over 0, 1 over infinity, and then you can have say infinity plus infinity and things like that. Some of them could make sense, and to make sense of especially the last two, there are certain rules that we can use as long as we understand the meaning behind it. So we know the definition of the infinite limit. Okay, so for example, we have the sum rule. So rules, sum rule, and so okay. So suppose we have a couple of sequences that diverge to infinity. Well, let me go this way. AN converges to A, and BN converges to plus or minus infinity. Okay, so we have seen rules of algebra just yesterday, rules of algebra of limits. So what happens with limits when we do algebra with those sequences, okay? So we're going to do the same thing again, but this time we do not assume that both of the sequences are convergent. Only one is convergent, the other one might be divergent to infinity. Does it mean that all is lost? No, we still can draw some conclusions sometimes. So if we're just careful. So the sum rule is an plus bn. Well, you can actually tell me what the limit is, just common sense. One sequence converges to a number a, the other one converges to, say, plus infinity. What's the answer? It's infinity. In fact, the same infinity. So if bn goes to plus infinity, then the first sequence wouldn't make any difference. The second sequence overwhelms the first one, and that it is the one that determines the outcome. Okay, then so you can have the constant multiple rule, say c times bn. Okay, so we take our sequence that goes to infinity and multiply it by c, a number. So let's say c is not equal to 0. Well, let's say it's positive. Let's just keep it simple. So c is positive. Then what's the limit? Nothing special happens. We take our sequence that goes to infinity, and just what we do, we stretch it or shrink it. But you know, that's the thing about it. Seems like we do a lot, but in reality, if we have something infinite, shrinking infinity does not shrink infinity. Okay, so sequence is shrunk, but the infinity does not. So if infinity, you cut the infinity in half, it's still infinity. Okay, so the result is then once again the same. Multiplication by a positive number does not change the outcome of a sequence that diverges to infinity. Okay, with products, similar. The product is similar. So an times bn. Once again, it will be plus or minus infinity as long as an is positive, or rather just a is positive. If a is positive, then we are not worried about the sign. That's the, I put the sign here, the sign of c and a in these two rules in order to make sure that we don't have to switch from plus infinity to minus infinity, which certainly would have to happen. But this is the simplest case, and once again you can see how the an is dominated by bn because an converges, and the second one diverges to infinity. So one is simply stronger than the other. So the last one is, well, the quotient rule. An over bn. So, okay, so where does an over bn go? It will be going to 0, right? So once again, domination. Domination. If you look at the top of the statement, we have two sequences, and one is convergent, which is, we like those. They well behaved, but in reality, the divergent sequence will dominate it, the other one when we do algebra with them. So we add, we multiply, we even divide, and you can see bn will bring everything down, or vice versa. You can think about this. If I take it upside down, turn it upside down, the thing will go to once again plus or minus infinity depending on the sign. Well, let's just say a is positive, so once again no change. So it's the sequence that converges to a number, and therefore it behaves kind of like that number. It doesn't do a lot of other things. So, but the sequence that diverges to infinity, that is a big one, and so it dominates everything that's happening. So these are the rules of limits based on the definition that we had. So they certainly have very precise proofs. But if you want shortcuts, you can see what you end up with is the ability to do algebra with infinities. Limited algebra. So for example, if I look at the sum rule, if I'm looking at the sum rule, what does it mean? It means I can say that a number plus infinity is equal to infinity. Okay, so as long as you understand that what's behind infinity is always a sequence. So a sequence and infinity is its limit. So we're not thinking of infinity as something that we can actually hold or manipulate like we do with numbers, but rather it is a limit. So behind every infinity is simply a sequence that diverges to infinity. Okay, so that's what we mean by that. But if you want to think slightly more informally, then that's what you might be thinking about. Number plus infinity is infinity, or plus or minus infinity, in fact, plus or minus like this. Okay, and then if I go with the constant multiple rule or the other one, product rule, regardless, it is what is a number times infinity is infinity. Okay, so once again, same story. Product rule, same thing. It is the quotient rule has interesting implication. It is a number divided by infinity is 0. Okay, a number divided by 0 is infinity. Okay, so these are the shortcuts. The algebra of infinities is what we're looking at. So same story. That number divided by infinity, once again, you understand that the numerator might be a number, but denominator is definitely a sequence divergent to infinity. Okay, and then the result will be, as a limit, will be 0. On the other hand, the last one, you also have to think in terms of sequences, and then denominator cannot be possibly equal to 0, but it could be the limit of a sequence that converges to 0. If that is the case, then the limit of that sequence will be infinite. Okay, so these are the shortcuts that we can take if we understand it. But notice that at no point you see here infinity minus infinity is not here. Infinity divided by infinity is not here. 0 divided by 0 is not here. As, 0 to the power of 0 is also not here. So some of the expressions with infinities or zeros remain indeterminate. So the indeterminate expressions are still indeterminate, and they are to be dealt with through limits, as always. Okay, so as long as we have these caveats on the right, so indeterminate, so these are no, and these are yes, I suppose. Okay, so we could do some algebra with infinities, and we can even divide by 0. You see it, right? Number divided by 0, it makes some sense. And what sense is it? Limits. Okay, so same with 0 divided by 0. It's also you could make sense of it if you have a specific limits for numerator and denominator. Then you work it out the way we just did. Okay, but what's on the left is kind of certainly more usable. Okay, so just be careful about indeterminate expressions, because they just simply might produce different answers. So if the sequences are not specified, then the answer is not specified either. That's what indeterminate means. Okay, so more properties of sequences and their limits. Well, how about the comparison test? There are several. So an larger than bn, larger than or equal to bn, for all n larger than n capital, then their limits have the same relation provided the limits exist. So careful about jumping to conclusions about inequalities between sequences. You can only argue this kind of comparison from comparison of sequences to comparison of their limits. It only works when limits exist in the first place. So two sequences may have inequality, but there is no way of speaking of their limits, because if their limit does not exist, it does not appear out of nowhere. Certainly not in this theorem. Theorem tells you what happens when everything is good to begin with. So it's a comparison of two convergent sequences. There is, however, interesting part to this. Once again, with the divergence. What happens with the divergence? So I have a limit. So suppose I have the same comparison, but now one of them is infinite. One of the sequences is infinite. So this is still assumed. And can we say anything about the limits under the when one of the limits is infinite? So Bn, n goes to infinity, minus infinity. So two sequences, okay, one is larger than the other. One of them goes to negative infinity. What does it say about the other one? Well, not like this. So two sequences, one larger than the other. Okay, so the point being here, I want to put a symbol between these two. One will be dragging the other one down. Which one is it? Is it Bn dragging An down to negative infinity, or vice versa? Or An is dragging down? So in other words, do I put this symbol or that symbol? N is larger, right? And both of them, or not both of them, one of them is going towards negative infinity, okay? Is this clear what I'm asking about? We want to draw a conclusion, but the challenge here is to figure out which way the logic works. So, well, let me answer my own question here. So An is above. If An is going towards negative infinity and Bn is below it, what does it do to Bn? Bn also has to go to negative infinity. Okay? But what if I replace with positive infinity? Then what? Then what? So the picture on the left is gone. Okay, so it applies to the previous example. So which way the arrow go? Well,
Maybe the opposite.
the opposite, right. The opposite, right. So Bn is large, but it's smaller than An, which means that An has got to be infinite too. It's like an inequality that also includes infinity. So say A is larger than or equal to B. Think about it. What could A possibly be equal to? It could only be infinity, right? And vice versa. So that's roughly the logic that we have. So as you can see, we can say something about the way the sequence diverges if we have this comparison to begin with. Okay, so that brings me to the squeeze theorem that you might remember from Calculus 1. And that one is better because we do make a conclusion about the existence of the limit. So in this example, it is assumed that the sequences converge. Okay, converge. Okay, but in the squeeze theorem, it is we do not. We conclude that they do converge. So Cn lies between An and Bn for all n larger than n capital. And we assume that the limits of the two sequences on the outside exist. And we know where they are, and they are equal to each other. Let's call it C. So as you can see, it's the same number. It's crucial that it is the same number, otherwise you don't have a real squeeze, but rather loose hold. So this is not a squeeze, because the sequence in between could oscillate wildly. Okay, so like say sine n actually lies between -1 and 1. So -1 is a good sequence, 1 is a good sequence, both of them are convergent. However, the one in the between does not, because it goes up and down. So that's not a squeeze. So the squeeze is when the limits also equal to each other. So that's what you see here, that they have the same limit. That's the conclusion. Then Cn converges, and its limit is C. Okay, so that is an example, a non-example of application of the squeeze theorem. An actual example we saw it a few days ago, or maybe a week ago or so. It is sine n over n. Remember this? Sine n over n. So if sine n is between -1 and 1, sine n over n will be between -1 over n and 1 over n. Okay, and then, well, as you can see, so then what we're talking about here, this is an, Cn, Bn, and the limit of 1 over n is 0. The limit of -1 over n is also 0. Okay, so then the condition is satisfied. So the limit of then sine n over n is also 0. In spite of all the oscillation, it will be 0. One more theorem that I mentioned previously, and I want to state it again. It's called the monotone convergence theorem. The monotone refers to increasing, decreasing behavior. So either it is an is less than or equal to n plus 1, that's increasing, an increasing sequence, or the vice versa, an larger than or equal to n plus 1, it is decreasing. So suppose we have a sequence that either increasing or decreasing, not both, okay, for all n. How should I put it? For all n, we have one condition or the other satisfied, so say A and B, A or B. Okay, that's better. Okay, then what? If an is also bounded, then it is convergent. Okay, so that's one of those meta theorems when there you don't find out anything about the limit or anything about specific about the statement. You just say that something happens without pointing out where exactly and how it happens. So we all say it is convergent. What is convergent to? We don't know. In what manner it converges, we also don't know. But it is a very useful theorem, and once we used it once already, for just in case you don't remember. It is this sequence an is equal to 0.999 n nines. So that's what our sequence is, n nines, which means what it is. The explicit formula will be 10 to the ninth, and here is, what's the numerator? So I'm talking about the decimal representations of numbers, and I want to point out, as I did last time, that sequence then converges because it is increasing, right? Think about it, it's increasing because you have more and more nines, so the sequence is increasing to begin with. Firstly, and secondly, it is bounded because it cannot go above 1. Okay, so bounded increasing sequence is convergent, and that is why we have a limit there. So that's why it makes sense. All I want to do is just to, in addition, to make it more explicit. So it is a fraction. So every one of these numbers is simply a fraction. The denominator is we divide by 10 to the ninth, and what's the numerator? No, 10 to the nth. 10 to the nth. What is it? Ten to the nth minus 1. Right? Okay, so n zeros. Yeah, n zeros means that it is 10 to the nth, which gives you n zeros and 1 in front, and then you subtract 1. So, so if you think about it, then it is really the conclusion that we make based on the theorem. So by the theorem, we made that conclusion, but also we can examine the sequence just directly. And if you look at it, we can actually make an argument why the sequence converges directly. So how do we know the sequence converges? In fact, converges to 1. So directly, can you make that argument directly? 10 to the nth minus 1 over 10 to the nth. Replace n with x if you like. So observe, it's exactly what we have been talking about. It's a fraction with both numerator and denominator both going towards infinity. So in that sense, it's infinity over infinity. But we get rid of this indeterminacy by means of what? Well, there was a trick in Calculus 1 for dealing with fractions like that. Hopital's rule, right? Hopital's rule is the easiest one to do with fractions. So remember what it is? Hopital's rule. That's right, yeah. So you differentiate both. So L'Hopital's rule gives me 10 to the nth minus 1 prime divided by 10 to the nth prime. And then, well, it doesn't really matter what the limit is because the derivatives are equal. So it's going to be 1, right? So L'Hopital's rule really works out very easily. So that worked out because the sequence was simplified. But in general, if you want to make sense of infinite decimals, that's how you do it. It will be increasing and it will be bounded. Okay, so this is we were just lucky with those nines that we were able to explicitly express the fraction as the decimal as a fraction, and then well, L'Hopital's rule worked, but this works out in general. It works out for every decimal representation. So you start with any sequence of digits, okay, infinite, okay, then you truncate it. That creates a sequence which is simultaneously increasing and bounded, and that means that there's a limit, and that limit is the meaning of that decimal. Okay. Okay, what else do we need here? Okay, so I want to also refresh your memory about a couple of things, about some limits that we're going to be applying when time comes again. So we haven't started the main topic, which would be here series, just sequences, but some of the famous limits that we have to just list them in order to refer to them when necessary. So we already had a few in the beginning, remember those specific sequences, but there are more limit of, say, the sine. What is the famous limit about the sine? Sine x over x. X goes to 0. What is it? Sine x over x. How about this sine x minus sine 0 divided by x minus 0? It's the same thing. What is that fraction? Looks familiar. Change of y in the numerator divided by the change of x in the denominator. It's called what? It's called the slope. So this is the slope. Slope of what? Of this line. This is 0, this is x. Okay, this is y equals sine x. Okay, and we divide run over the run, rise over the run, right? So run, rise. Okay, and then we take its limit, which gives us what? The derivative of the derivative. The answer is the derivative. So the limit of the slopes of the secant lines is the tangent line. So this is the secant, right? And then at the end we have the tangent. So as x gets smaller and smaller, we have this behavior. The secants rotate, and eventually they converge towards the tangent. So that's just the things work out actually the opposite way. You try to figure out what the derivative of sine is, and that's how you do it. You express it in terms of this fraction, moving from right to left. So this is sine x prime at x equals 0, which you should know what it is. The derivative of sine at 0 is what's the derivative? Should be 1. Yeah, because it's cosine x at x equals 0, and it is 1 indeed. So, which means that the slope of the tangent line is 1. So it means at 45 degrees. So it's a nice function actually. So it crosses the x-axis at 45 degrees like this. So this is 45 degrees. That's what we discover about the function. To begin with, before you compute all the rest of the derivatives of sine, this is what you do. You look at just one point, and then figure out why the answer is 1. We cannot, you don't refer to the derivative as we just did, but rather working backwards, and then we try to find what the derivative of sine is, and so we work our way this way, okay? And then there is a way to do it. why the limit is equal to 1, and the answer is, we almost did it just now. Okay, so sine lies between -1 and 1, so in other words, we use the squeeze theorem. And that proves that the result is equal to 1. That doesn't work. Hold on a second. No, I'll have to take that back. So it is done with slightly more trigonometry. You actually need more trigonometry in order to prove that this is equal to 1. So, well, this is strictly speaking, so that is strictly speaking calculus 1, so we're not going to do it. So the squeeze theorem only helps us in this situation is whenever we look at the limit as actually when x goes to infinity. Okay, so this one, however, like I said, we cannot use the squeeze theorem. We need more than that. We actually have to look at the definition of sine. So not just the fact that it lies between -1 and 1 is really not that important. What I mean, but now we know that it's equal to 1. What the point of this was to restate this limit, this famous limit, this one, restate it in terms of sequences. And one way to do it is simply put a sequence on the graph, as I suggested, like this. And so then sine xn over xn, n goes to infinity, is equal to 1 for any sequence xn that goes to 0. Okay, so that's direct restatement of our limit. So it is certainly the original statement is more compact because it's just, you don't have to refer to sequences. You look at all x's converges to 0, and it includes all the possible sequences. But there is another way. If I specifically pick a sequence that goes towards 0, so pick xn is equal to 1 over n. It is definitely 1 convergent to 0, so that works out. So then we have our limit becomes sine 1 over n over 1 over n is 1. Okay? Or we have now a new statement, which is n sine 1 over n goes to 1 as n goes to infinity. Okay, so it's the same statement, just put in the form of the limit of a sequence. Okay, so we have just a couple more of these left, so let's talk about it tomorrow. So there will be still another homework tonight.